All right, then let's get started, guys. Now, so yesterday when we started off the organic section, we spent a bit of time looking at nomenclature. That was supposed to be revision, believe it or not, of everything that we did at stage one. What you're going to need to do is to work your way through the textbook questions and the two handouts that I gave you. Now, that's not the only thing that I gave you. There's a whole lot of other resources that you should be accessing in sector as well. And Jack, this is for you. You better make sure that you catch up with the work. Got that, Jack? All right, now, so we attempted to get to what we called in the textbook, the heading for it is called physical properties. So, physical properties of organic compounds. Now, the physical properties that we're really only worried about are fairly small. Okay, there's not a huge number that we have to worry about. So the physical properties that we pick up in the text are things like their melting point, if they're a solid, where in most cases they're boiling point. Okay, so we look at those properties. Is it a low boiling point? Is it a high boiling point? That's the first thing that we look at under the physical properties. And then we simply look at their solubility in water as being obviously the universal solvent. Okay, for us. It was the universal solvent last week and it's the universal solvent this week. All right, now, any ideas about what we have to focus on then with your current knowledge? So what do you think we need to look at? What have we covered so far in the course that would help us understand these two characteristics?
Gotcha.
Will?
Secondary bonding.
Secondary bonding. Okay, so it comes back again. So we need to remember everything we did about secondary bonding between molecules. And I'm not going to run through that again, right? But just to highlight the secondary bonding that we did. The first type that we did was H-bonding. Okay, most important. What was the requirement for H-bonding to occur? What do we need for a H-bond to be set up between molecules or within a molecule? Will?
NH-OH.
Alright, so we're after an OH on separate molecules. Okay, or it can be between an N and a H on separate molecules. We also have a fluorine and a hydrogen. I could put them in, okay, but I can't remember that there's been many questions that involve secondary bonding between a fluorine and a hydrogen. Has there been any? Don't think so. So we're looking for compounds that have got OH groups in their structure or NH2 groups in their structure. And they were two functional groups that we talked about, or didn't go into much detail, but they were the functional groups that we talked about yesterday, alcohols and amines. All right? So wherever they are, you would assume that we're going to get H bonding in the structure. Cool.
Didn't you also say something about COO or CW?
Yeah, carbon I'll come to when we get to that. All right? So H bonding is the first type of bonding that we looked at stage one, and we're going to do it again in stage two, and we did it in the small molecule section this year again, didn't we? All right? So we've covered that heaps of times already. So the next was dipole-dipole bonding. And when you think about dipole-dipole bonds, Clint, what do we need for dipole-dipole to be set up? How do we tackle dipole-dipole bonding? Two different poles. Yeah, that means it's going to be a dipole in a molecule. But if I've got several molecules, two molecules, what do we need, Jack?
Difference in electronegativity.
Yeah, there has to be difference in electronegativity, Joshua. The what? Attraction of the delta sides. Delta charges. So what do I need before I get a dipole-dipole set up? If I have two molecules, Will? Polar. You've got to be polar. That's what I was after. All right. So we have to have a polar molecule and we obviously have to have another polar molecule. Now these molecules, as we said, and as we did in our demonstration last year when we were mixing alcohols at varying chain lengths, we said that these molecules obviously have to be polar molecules for that to happen. We'll talk about chain length in a minute. So if this is the delta negative, if that's the delta positive in a polar molecule that we should be able to work out, because we've done chromatography this year as well, that's going to align with the delta negative and the delta positive with the other polar molecule. So you can use that. It's a little bit like a north-south magnet arrangement. So that's going to be how we conceptualise a dipole-dipole bond. So normally, if we've got H-bonding, we're going to automatically have dipole-dipole. But it does depend on the chain length. Alright? Third type of bonding we need to be aware of is dispersion. Now, where do we get dispersion forces occurring? What types of molecules do we observe dispersion forces with? Sorry? Non-polar. Alright, so we've got non-polar. I wonder if Mason's awake. Do you think he's awake or is he still in bed? I wonder if Mason is sick, isn't he?
Yes, yeah.
So Mason, you better make sure you watch this too. Alright, non-polar. Over here, non-polar. Now, does anybody remember the terms that we had to understand and be able to explain if we're going to get dispersion forces set up? Temporary induced, good. So we use the words temporary, and then we use the word induced dipoles. So how do we get a temporary dipole set up? There's a few ways. Mr. Marty?
Particular instant in time.
That's a nice surface you've got there. How do you get a temporary dipole?
Particular point in time.
Good.
Electrons might be one point more than the other.
Good. So we can take a snapshot in time of any molecule, and we're assuming that because electrons are moving, at some point, in theory, there might be more electrons on one side overall in that structure than what there is on the other. So we get a snapshot in time. That becomes, for the purposes of this, this explanation, a delta negative. Electrons are sort of sucked to one side. Alright, well, they're not actually sucked, they're just randomly there. Alright, so delta plus. Alright, this is my temporary dipole. There it is, very temporary. Alright, what was another way how we could actually get a temporary dipole set up? Well, collision between molecules. So when they bump together, the other theory is that electron clouds are distorted. Just like when you have an accident between two cars, normally they're distorted in some way. The panels get dented and all sorts of stuff. So, temporary, the outer electrons are going to come together. Some of those electrons are going to be moved to different locations. So we could argue the temporary dipole either just randomly or due to collision. Okay? Not sure. I think the textbook talks about randomly, don't they? They don't talk about collisions, do they?
They don't talk about both.
They don't, do they?
No.
Do they talk about both? I think we only do one in the book. Alright, anyway. Alright, temporary. Sitting next to it is another molecule, okay, which is initially non-polar. David, what happens to this one? Good. What do we call this one? That's the induced dipole. And so what actually happens is that because this is delta negative, okay, let's do that the other way around, okay, because this is a delta negative, obviously it pushes the electrons to one side. It's going to repel, light charges repel, a little bit like we use for Vesper theory. So it pushes electrons away from one side, and so it sort of causes this very weak dipole to be set up, and we call the second dipole an induced dipole. And of course, then we simply say, oh, that's not happening with one molecule, that's happening with many. So we have a whole series of temporary dipoles, and then induced dipoles, and then induced dipole induces another one, we get sort of a chain reaction set up. Okay, that's the theory behind dispersion. Everybody cool with that one? All right, said I wasn't going to explain the concepts, but we've just gone through it just to refresh our memory. So now we look at the same idea. Oh, what's the other form of secondary bonding? Iron dipole, but we don't look at it here. Why not? Because there's no, yeah, we're not dissolving ionic compounds, okay, in this instance, so we don't even look at that, but it's still one of the ones that would be the fourth one. You have to have it again in your memory, wherever that is, all right, in there. All right, so now we look at covalent, so the secondary bonding, I should say, within all of the organic molecules, and there's a few things we have to consider. So what things are going to affect the boiling point? And I'm going to narrow it down to the exact, not the exact, everything will focus on one or the other of these things. Number one is basically the type of functional group in the molecule. And we're going to start to look at all the functional groups individually over the next few lessons. Okay, so type of functional group of the molecule. What I mean by that is, if we just look at the functional groups, just choose a nice, pretty colour. So I know Jack likes, Jack, purple for you, purple, there it is. All right, we're laughing at. All right, all right. Type of functional group. So, and I want to highlight the functional groups that we're going to be doing in the course. So, we're going to have alcohols, we're going to have aldehydes, we're going to have carboxylic acids, we're going to have, what else are we going to have from last week, yesterday, I mean? Amines. Yep, we're going to have this sort of functional group, ketone. We're going to have amine, so it's an RNH2. What else are we going to have? Another functional group we're going to look at. We actually do amides, that's the amide functional group. And we're going to do also esters, OR-. So we've got alcohols, aldehydes, carboxylic acids, ketones, amines, amides, and esters. So they're all the functional groups, all right, that we're going to tackle in the course of this massive topic on organic. All right, now, not only the type of functional group is going to determine the melting point or the boiling point, it is the number of functional groups. So what we mean by that is the more OHs we have in a carbon chain, we would expect the more soluble the compound would become in water. We did that demonstration last year. All right? So it's not just to do with the functional group, but if I've got lots of them, it becomes very soluble. Example, very, very quick example, is something like this. So there's an example of a simple alcohol. 1, 2, 3, 4, 5. 5 carbons in the chain, soluble or insoluble in water. What is it? Pentanol, insoluble. Okay? Why is it insoluble? Long carbon chain. The non-polar dominates over the polar. Okay? Now, if I do this, what do we think now? Soluble or insoluble?
More soluble than before.
It's more soluble than before. Okay? Good answer, Will. Alright? 1, 2, 3, 4. Still got that 4 carbon chain there. Alright? It just happens that we've actually broken up that big long 5 carbon with another OH. So by putting another OH, it's certainly going to become more soluble. Do you think it's going to be totally soluble in water? No. Probably not. The solubility will be up to so many grams per 100 grams of water. Alright, so the solubility would increase. Initially we might have said it could have been, say, 5 grams per 100 mils of water, it'd be partially soluble. But then of course if we did that, it might go up to 20 grams per 100 grams of water. Who knows? we need to look it up, okay, to work out the exact answer. So lots of functional groups means, depending on what the functional group is, more solubility. Because obviously it can H-bond here, it can H-bond here if we're looking at water as being a solvent. Alright, so the number of functional groups is something else that we have to consider. What else do you think we have to look at in terms of solubility of molecules or their forces of attraction? Length of carbon chain. Alright, so the third thing is the length of the carbon chain is very important, and we just had that example before I rubbed it off the board. So long carbon chain. Okay, now if it's a long carbon chain, non-polar, non-polar, what do we think is going to happen with compounds that have got long carbon chains? They're going to have a high boiling point or a low melting point? High. Alright, so we'd expect a long carbon chain molecule to have a high boiling point. Why? Because it's related to its molecular weight. We've got to put that there as well. Molecular weight. The greater the molecular weight of the compound, which is sort of keeps the carbon chain length, okay, we would expect the more what sort of bonding we're going to have in the context, when we're talking about large molecular weights, where are they going to tend towards? They're going to tend towards dispersion, all right? So the length of carbon chain, molecular weight, sort of connected, all right? So the longer the carbon chain, then we have to argue the greater the dispersion force. When I say greater, we didn't really answer that question. So why is it that as the molecular weight increases, the boiling point and the melting point goes up? Will? David? There's more of it to... We looked at it... Actually, we haven't done this yet. I was thinking, okay. But when we do things like soaps and detergents, and we look at triesters, and we talk about, you know, why is, for example, why is olive oil an oil, and why is butter solid? It's something to do with the dispersion forces on the chain. So, the longer the carbon chain, the greater the number of forces, because there's more electrons that are being moved. So if you've got lots and lots of electrons, you would assume that you're probably not going to get one pole set up. There's going to be a whole lot of maybe temporary poles on the carbon chain. All right, that's how we argue that one. So if we're pushing lots of electrons around, you have to assume there's going to be lots of opportunities for bonding all the way along the chain. Okay? And you can use the analogy, you know, of the forces of a large molecule, like a semi, for example, a large mass vehicle, heading into a large mass vehicle, there's lots and lots of damage. They're both carrying a big weight. Right? So if you relate that to the number of electrons, lots of moving electrons, more forces, then you shouldn't be too bad with that. Alright, so that's really what this chapter looks at. So it covers functional group, the number of functional groups, the carbon chain length, and molecular weight. And that's, if you can nail that, if you can understand those concepts, then this is pretty simple. All right? Dave?
Can you explain what you said?
What is?
So you said the longer the carbon chain.
Yep. Let's look at an example. How about that? All right? If you flip over to 248, all right, and we have to compare the same types of molecules, and I'll explain why we're going to do this in a minute. So at page 248, halfway down it's got group 1, group 2, group 3, because the textbook then starts to go into, well, how do alcohols bond with themselves? So does a small carbon chain alcohol have a high bonding point or a low bonding point? Okay, and then we compare, okay, with the same molecular weight with an aldehyde, has that got a high bonding point or a small bonding point? So before we start to launch into that, just to answer David's question, when we start to look at all this stuff, we have to have something that's common. And we normally work on molecular weight. So we have to say, if we're going to compare the bonding with compound X and compound Y, we've got to have the same molecular weight. Then we then look at, okay, what's the difference? Typically it's the functional group that's different. So if the functional group's different, okay, then we can attribute the bonding to the functional group. You understand what I'm saying? So I can't compare a 20 carbon length chain with one OH and then a with a 5 carbon chain length with an OH. It's fairly obvious the 21's going to have a higher bonding point. So I need to compare similar molecular weights. Now, what was your question again? I got sidetracked. What was it, Dave? Oh, why is it? Yeah, okay. So, and I said let's look at these. So here in the book, we'll look at the one example, which is propan-1-ol. So here it is, 1, 2, 3, and OH. So propan-1-ol has got a boiling point of 97.2. So the boiling point is 97.2. Now its molecular weight is given, or its molar mass, is 60. Okay? Then we have got hexane-1-ol. So we double that, 1, 2, 3, 4, 5, 6. And we're told the boiling point of the hexane-1-ol is 157.1. And of course, its molecular weight is significantly more. Its molecular weight is 102. And then it goes on to decanol, 229. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Boiling point 229, and molecular weight is, in this case, what is it? It is 158. So the trend is what you'd expect. In other words, if I increase the molecular weight, look what happens to the boiling point. It goes up, all right? And your question was why, correct? So we have, along this very, very long carbon chain, not worried about the OH, because that's not going to be anything significant at all, all right? So if I'm going to mix this molecule with another molecule, okay, if you can imagine a whole lot of these molecules being side by side, all the way along that molecule, non-polar, we know it's a non-polar molecule, there's going to be a lot of dispersion forces. Lots of electrons are going to be pushed around in this molecule. As we go to a shorter molecule, well, much tinier molecule, okay? This is actually a polar molecule, so we know we're going to get H-bonding here. We're also possibly going to get some dispersion force on that side of the chain as well. All right? But, although we've got H-bonding here, and we probably have a small amount of H-bonding here, we can't compare a molecular weight of 60 with 158. Okay? So we can do it within a functional group, which is the alcohol functional group. We expect that trend. And you'll see in a minute when we go through an example that we compare just functional group changes. Everybody cool with that one? So big long carbon chains is saying, yep, all right, we've got to get more dispersion forces. So the molecule tends to become more non-polar, regardless of what the functional group is. Now, let's just move and we will look at the examples in the book, because then we really only have to then look at which functional groups form what sort of secondary bonds, because everything else is going to be dispersion, isn't it? All right? And then we look at how many OHs or how many functional groups we have. So we look at the bonding with the molecule with itself first. And so we'll look at propan-1-ol, propanal and propanone. 3 functional groups. So we've got this one, 1, 2, 3, and then we've got the propanal, and then we've got the propanone. So they're all similar molecular weights, but if we look at their actual boiling points, it's 97, 47 and 56. This one here is 97, 47 and 56. All right, now, not the trend probably we would have expected, okay? They're all similar molecular weight, and we can say, all right, if I'm going to look at propanol bonding to propanol, it's fairly large. Why is the bonding point for the propanol large? Why is it the biggest of all three? Well, it's going to have H bonding in structure. All right. So straight away, you can see that this is going to have H bonding, and it's also going to have dipole-dipole. Sort of stands out. All right. Now this one, aldehyde functional group. Okay. Is the aldehyde functional group going to have H bonding with itself? It's not going to H bond with itself. Okay. It's got no OHs. I think we've had this question before. All right. So, can a H bond with water? It can H bond with water. Okay. The difference is water's got an OH in its structure. We'll do that one in a minute. All right. But it can't H bond with itself because it's got no OHs there. All right. So I can only have a H bond if I've got an OH on one molecule. This is going back to Will's question, and a carbonyl next to a H, all right, somewhere in the structure, because that becomes delta negative and that becomes delta positive in that carbonyl group.
Wait, does it have to be C, O, and H?
Yes, because we'll look at ketones in a minute and see if ketones are soluble in your C. They're pretty much not very soluble in water at all. All right, this is our example here. All right, so of course, what sort of bonding have we got there?
Dispersion.
We're going to what?
Oh,
In a short carbon chain, we're probably going to have dipole-dipole. Well, probably we are. Dipole-dipole. If the carbon chain was longer, I'll probably add dispersion as being a dominant thing there, but it's not. This one, very weakly. All right, and again, this doesn't always follow the trend. Okay. So here we've actually got acetone, all right, and again, the only thing we can have is a slightly polar molecule, and we're going to get some dipole-dipole there. But they're all similar molecular weights, all right? Now you'll see the trend, because in the book then it goes up to hexanol, hexanal, and hexan-2-one. So hexanol is 157. Now it follows a trend. Hexanal is 128 and hexanone is 127. All right? So the trend is the same pretty much. This one, these two here reversed. All right? But similar in terms of the trend based on similar molecular weights. Now, we do that throughout this section. So then we compare, if you look over the page, all right? Keep going. Oh, no, not going too far. So then on page 251, we're looking at primary alcohol, aldehydes, ketone, carboxylic acid, and primary amine. So, while we've got these on the board, these are the ones that are most likely going to have a higher boiling point, these functional groups. Anything with an OH is going to be able to H bond. We'd expect that to have a high boiling point, wouldn't we? Compared to other functional groups. This one here has got also going to be able to have H bonds within its own structure, bonding to itself, yeah? This one here, the amines, I'd expect also, if I'm comparing apples with apples, have a H bond. I expect these ones here, the amides, to have a H bond in their structure. So if I had all of my functional groups and all the same carbon chain, similar molecular weight, I would be predicting that these ones here would be those ones that would have the higher boiling point. Can I get H bonding in an ester structure bonded to an ester? No. I can get maybe some dipole-dipole. Okay? Ketone to ketone, dipole-dipole. Aldehyde, dipole-dipole. So we run through all the ideas of what happens when I try and bond one organic molecule with another. Okay? Now, back to the other question that we had before, which is about their solubility in water. Because we need to be able to draw these bonds. So you actually have to show the H bonds. Okay? Now, let's just run through a couple of examples. We'll be very original and we'll use the examples in the textbook. So let's look at solubility of water, and we'll jump over to where we'll jump over to. All right, we've got it page 252. Okay, so 252, and we'll just clarify how that happens with the solubility in water. All right, before we do though, if we were going to do it with a straight alcohol, it comes straightforward I think, I'd need to then draw the alcohol OC. I've got to show in all of the secondary bonding, I've got to show the polarity, and then I've got to show, okay, the H bonds. And of course, that's not the only structure. I can keep on going. I could be drawing that down here. And all you need to do is to make sure that the delta negative is attracted towards delta positive, and you show the polarity of all of the individual molecules. So we can keep on going with that structure. I've just used a couple, all right, to show the H bonds, but there could be a whole lot more there. We've already got that one. If we're going to look at, say, a carboxylic acid, we do the same sort of idea. O, H, H, O, and I'll draw it upside down, like that. And so I'd expect the same thing, delta negative, delta positive, delta negative, and show the H bond here, and show the H bond here. Okay? Now, this would also be a delta positive, and that would be a delta negative. Wouldn't it? Yeah? So I could also draw another compound down here, same deal, alright? Try and stick with the same carboxylic acid, delta negative, delta positive. So I could actually do this, could also get a H bond off that oxygen as well. Because the OH can allow me to form a H bond with a carbonyl. We'll see that happen in a minute when we do aldehydes. Alright? So we've got that idea, but when we try and a lot of people get confused with this one, they try and show an aldehyde H bonding, and they draw it like this to show what they tend to do. So they do their aldehyde, and they do that, and then they do that, and they do delta positive, delta negative, and for some reason make that delta positive or delta negative, okay? And they show it like this, H, C, C, and they say that this, they call that a H bond. Okay, and we know, we're a bit smarter right now, right? So that's not a H bond. No. Okay, because it's come from in this instance here, alright, this is a carbonyl group, it's not an OH. I have to get an OH in order to get a H bond. See the difference? Here it is, I'll highlight it in red. So this comes from an OH, is the basis for my H bond. There's no OH here, and there is no OH here. So it's not a H bond. Alright? This is an example of a dipole-dipole bond. But if I change it a little bit, if I look at aldehydes, and if I now put the aldehyde into water, okay, I can have this set up. So just do that a little differently. So it's H, O, and then H, delta negative, delta positive, negative, positive. So if I actually look at this, it can now, there it is, okay, water has got the OH. So here it is, okay, and that can H bond with the oxygen on the aldehyde functional group. Everybody okay with that one? All right. Now, of course, when I do things like, when I start looking now at these compounds, okay, esters can only do dipole-dipole, there's no H bonding, without me having to draw everything, all right? If I'm going to do this one here, I would just expand out, delta negative, delta positive, and I have my amine group up here, and delta negative, delta positive. There is my H bond between the amines. And you can elaborate on that yourselves, all right? So that's the things that you need to sort of get right, okay? Got to be able to draw these bonds and explain the actual bonding point based on the functional group. All these ones are going to have H bonds inside them. This one will obviously be able to H bond, this one here, will H bond with water. Do you think, the ketone we're going to check, won't we? Okay, ketone. Do we think ketones are going to H bond with water? What do we think? Ketones and H bonding. Okay, so if we look at everything that's happening in here, there's no examples, okay, no examples of ketones that are going to H bond. All right, and the reason is we've actually got a carbon and a carbon and a carbon on the side of the carbonyl. Okay? So obviously this delta negative and that delta positive is not enough, okay, to make a H bond with an OH compound. David? Yep. Which one? Oh, this one? Yep. This is C double bond O, yep. This is H, OH, that's water. Yep. So here's the OH in water. Alright? As long as an OH in another compound, and if it's an aldehyde functional group, okay. Also, I didn't mention this one, not just an aldehyde, it could also be, a carboxylic acid, yeah? So I could also, if I had water up here, I'm also going to get a H bond there, aren't I?
So it just can't be another,
just can't be a carbon.
Yeah,
If this is a carbon, it's not going to actually be able to form a H bond.
why?
Because it's obviously not pulling it across enough to make it polar enough. Again, it's to do with the polarity of the molecule. Alright, questions with that one? Alright, we will leave it at that then.